Good evening, everyone. So this is your good evening. So this is your last tutorial, and this is your day 9 of the GIAN course. And today we will be actually performing edge couple stacking, and then we will have a kind of glimpses of how the seismic interferometry is done in terms of cross correlation of the ambient noise using the Gutenberg report. So before we start upon, I would like to show you, I have already shown you that paper by Zhu and Kanamori, and you might have read it. So because yesterday our OneNote was not working, so I could not explain you the exercise tracking that well. So I will start with exercise tracking first, then we will look at the data, and then we will look at how the exercise tracking can be performed using the MATLAB code that is within the process RF MATLAB by IW Billing. So exercise tracking. So as I told you, it is given by Zhu and Kanamori in 2000. So let's suppose this is the surface of the Earth here, and you have a seismic station located at the top of the surface. So this is your receiver, you may say, and it is basically installed in the field for a large amount of time, and then it is recording data for quite a few years. So it must have been recording teleseismic data as well. And let's suppose it has recorded many number of earthquakes. So this is your, let's suppose, earthquake 1, and the data has been recorded by this station. And let's suppose this is your earthquake 2, and the data has been recorded by the station. And this is your earthquake 3, the data has been recorded by the station. Okay, so likewise, it has been recording a sufficient amount of data, and maybe this is your earthquake N, and that has also been recorded by the seismic station. So I will sometimes receive a seismic station, maybe sometimes seismometer. So all means same here, and from all these earthquakes, all these earthquakes are we are choosing here are teleseismic events. That means these are coming from a distance of more than 30 degrees, and teleseismic event we are considering because we want to have the tip of angle smaller so that it can dip down to the mantle structure and the upper mantle structure. And so from these earthquakes, you can also calculate respective receiver functions, PS receiver functions. So PSRF1, and from earthquake 2, you can compute PSRF2. Likewise, you can compute PSRF3, right? And for this, you can compute PS receiver function NH. Okay, so after you have computed your receiver functions, then you can start with your edge couple stacking. So let's assume that your receiver functions may look something like this. So maybe your PSRF1 may look something like this. This is the direct phase. This is your P2S converted phase. Here you have PPPS phase, and then there is a negative polarity phase. That is the last phase, which is the PSPS or PPSS phase. So this is the direct P wave. This is a P2S converted phase, and here you have PPPS phase, and here you have PSPS plus PPSS phase. So both of these multiples, PSPS and PPSS, arrive around at the same time in the receiver functions and having the negative polarity. So it is PSPS plus PPSS. Likewise, you have another receiver function, PSRF2. Okay. So PSRF2, again, this is direct phase, this is PS converted phase, this is your PPAPS phase, and likewise the last phase. And you can also compute PSRF3. Okay, and then so on. And the PSRFN, the last one. Okay, so for all these receiver functions, because you are actually having a telespecies P wave energy that you are actually processing by windowing the seismogram around P wave and then doing the rotation, then the convolution to compute the receiver function. So this for each earthquake, this P wave will be having a specific ray parameter. So this one will be having P1, maybe this one may be having P2, this one will be having P3, or maybe this one will be having PM. So we can write the parameter in front of them. So this is P1, this is P2, this is P3, and I know you all know about what is ray parameter from the classes that we've taken previously. So this is this is PM. Okay, and so now you know the formula of arrival time of P2S converted phase. So the formula for P2S converted phases are like this: EPS is equal to H in bracket under root 1 by Vs square minus P square minus under root 1 by Vp square minus P square bracket close. Likewise, you have the formula for arrival time of P F phase, that is H in bracket under root of 1 by Vs square minus P square plus under root of 1 by Vp square minus P square. And the last formula that you have for the arrival of S phase plus PS phase. So that will be equal to 2H under root 1 by Vs square minus P square. Right. So these are the formulas that you may have to calculate this arrival time of these different converted phases. So what actually you will be doing? So from the class yesterday's lecture, we came to know that the parameter that affects the H value the most is the VP/VS ratio, right? So what we are going to do, we are creating all this travel time as a function of H and VP/VS, right? So in order to do so, what I will do, I will take VP out of it from all the equations, VP out of it. If I am taking VP out of it, then I will have to multiply by VP square, right? Likewise, here also I will take VP out of it and then multiply by VP square. Sorry, it will become 1. So VP square, you must say, this is all VP square. Likewise, again, here I am taking VP out. So this is your VP square and VP square. Right?
So,
yes.
So in these equations, the Vs is constant and Vp is constant, right? And so for each earthquake,
No, not VP constant.
Vs are constant, right?
No, ray parameter for P wave for each earthquake is constant.
Okay. Yeah. So I'm saying that the VPVS are constant. The only variables are H. And
No, VPVS is not constant.
so it's not okay. Okay.
It's not constant. Let me finish, then you will
Okay.
get to know how it is working.
Okay.
Okay.
Okay, sir.
Okay. So if I will rewrite, so you can see I have created these formulas TPS as a function of VP as a function of H and VPIVS. So TPS as a function of H comma VPYVS is equal to H by VP in bracket under root VP by VS whole square minus VP square and P square minus under root 1 minus VP square P square. Correct? Likewise, we have created formula T, P, 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 S, H as a function of H, VP by VS, and that will be equal to H by VP in bracket under root VP by VS whole square minus VP square P square minus, sorry, plus under root 1 minus VP square P square. Correct. Likewise, I can write the third formula for the third arrival type, that is PPSS plus PSPS, that is again as a function of VP by VS, and that will be equal to H by VP, 2H by VP in bracket VP by VS whole square minus VP square P square. Okay, so now you can see I have written all these formulas in terms of H and VPIVS. Now, what we are going to do, as we have seen in my previous lecture, that VP does not affect much the value of H and VPIVS. Okay, does not affect the value of the thickness of the crust. So in that sense, I can take VP as constant. Okay, or you can take VP value from the previous study for the average crust. VP is the average PV velocity for the thrust. So this VP you can vary. You can take either from previous studies or maybe from some refraction or the wide angle surveys, or you can just assume it. Okay, or maybe you can take some you can if there is no studies available, then you can take in between any value from 6.0 to maybe 6.6 kilometer per second. That is the general value that typically found for the average crust all over the globe, with some exceptions. So so this value, you can take any value in between that. And then what you can do, you can make a grid between H value and VP by VS ratio. So you may say like why we are considering VP by VS ratio. As I told you, it actually tells many things about the chemical compositions of the rocks that are available within the crust, or also the if you know the value VP by VS ratio, then maybe possibly you can predict what kind of rocks may be available in that area. So from VP by VS ratio, you can convert it easily to the Poisson's ratio. So that Poisson's ratio is basically very important parameter in our sciences. So you can make a grid between H and VPIVS. So maybe you can vary H value uh, uh, to around like if maybe between from you may say like 20 kilometer to maybe 60 or 70 kilometer, maybe with a step of uh, zero point 0.1. Okay, and VPIVS you can vary possibly in between maybe 1.5 to with a step of maybe 0.01 to 2.0. Okay, so so this is a grid that for various combination of H and VPI/VS ratio, you will calculate these arrival times. Okay. So, if I will make this grid, so here you have H, here you have VPI/VS. Okay, and VPI/VS is varying from 1.5 to 2, right? And here the H is varying from 20 kilometer to 60 kilometer. Okay, and you have made a grid like this. So at each grid point, you have made this grid. So for each grid point, you are going to calculate TPS, TPPS, and TPSPS. Okay, for each grid point. So if you are, let's suppose the first grid point is maybe 20, 1.5. Okay, and maybe so for this particular combination, you can calculate from these formulas, right? From these formulas, you can calculate your TPS value. So TPS value you can found. Okay, likewise TPPS also you can found, and you can also found TPSPS. Okay, so when you do so, when you found that value, you calculated this value for a first combination of HVPIVS, then what you are going to do, you will, of whatever value of TPS you will get, that value you will try to locate on your receiver function. So let's suppose this is the value that you got, and this is the value that you got, because these are the times here. Okay, on axis you have times. Okay, so this is the value you got, this is the value. So corresponding amplitude you will sum and average. Okay, for TPS. Likewise, you can do the same thing for the TPPS. Do sum and then average. So after you do so for the first combination, then you will have this formula. You will apply this formula SHK that I showed you yesterday will be equal to W1 amplitude of PS converted phase plus W2 amplitude of PPPS phase minus W3 amplitude of PS plus PPSS phase, right? So this negative is there because you know your phase, these phases actually are of negative polarity. So in the equation, you will keep it as positive so that you can sum them up. So, and one more thing that you need to remember about these weights is that this W1 plus W2 plus W3 should always be equal to 1. So you assign these weights in such a manner that the sum of all these weights should be equal to 1. And also one more thing that you must remember, that W1 should be greater than W2, W2 should be greater than W3. Okay, why? Because in receiver functions, T2S converted phase is generally the distinct phase, which is very much clear phase if you compare it with the other arrivals. Likewise, the second phase, that is your PPPS phase, this one is much clearer than the third phase, but it is less clear than the first phase. So that is why the less weight will be given to this one, and the least weight will be given to the last phase, last multiple. Okay, so you can choose any combination, like maybe this, maybe you can give 0.5, maybe this W2 as 0.3, or W2 as 0.3 and W3 as 0.2, or maybe the 0.6, 0.2, or maybe 0.3, 0.1, likewise. Okay, so after you given those weights, and then for first combination, you will calculate this value SHK. The first combination, this one, you will calculate this value SHK. Likewise, for second quality, so you will keep that value of SHK here. Okay, you will keep it here onto the grid. Likewise, you will calculate the SHK value for the second combination of SHK on the grid and keep that value over here. Likewise, for the third combination, you will calculate, then keep it here. Likewise, third combination, you will keep it here. Likewise. So for all the combination, all the possible combination of H and kappa, you will calculate the value of SHK and then keep it on the grid. Then you do interpolation to make a smooth contour map of for various combination of H and VPIVS. So finally, the output that you will see would be looking something like this, as I shown you in my previous lecture. Yeah, it will look something like this. Okay, that this figure that you are seeing here. Okay, here you have VPIVS, here you have H, and then after you incorporate all the SHK value and did interpolation, and then you will get this kind of figure. And wherever the SHK value will be highest, that will be the value for the corresponding value of H and VPIVS. That is the best value, which actually represents your crustal structure, average crustal structure. Okay, so that is how this H-kappa stacking works. So I hope uh, Mr. Ghosh, do you still have any question about the constants thing?
Yes, sir, that's fine. I was just wondering something else. This is good. Thank you.
Okay, thank you. So this is how the H-kappa stacking should work. Now let's move on to see the real data example. So now I am going to open the mobile extern again. I hope my terminal is visible to you. Now I will log into my system in the lab. Now it is connected to the system. I will go to the directory where I have kept an example. And I'll go to the process RF MATLAB. And then there is a folder with the name depth mapping. I'll open that. No, test script. Yeah, test script. And then there is test depth mapping folder. And now I will open my MATLAB here. So now my MATLAB has opened, and let's look at the file. So basically, I'm going to perform. So yesterday we have seen how to compute the ratio functions for both of the station ISM and Bocaro. Today again we will be considering the same stations, but today we will be seeing how to do H-kappa stacking. So you can see this is the code for H-kappa stacking, which is actually provided by IW Bailey, and he has actually kept he has made this function test HK IWB as it did because this code might have been created a long time ago. That's why some versions are keep on coming. So I have tested it already, so it works well. So you can see the H values that they are varying is in between 20 to 60 kilometers with a step of 1. And kappa value that they are varying is in between 1.5 to 2 with a step of 0.01. And the weights that they have given for W1 it is 0.7, for W2 0.2, and 0.1 for W3. And the average BP for the crust they are considering is 6.3. And this is the directory where this is the path to the directory where my data are located, and then these are some directory stuff. If there is any unwanted directory, then it will get removed. All this stuff it is doing. Now, then they are actually performing some steps, basically to identify different pages that are available on your receiver functions, and then they are performing their HKFA stacking using this function HK stack underscore IWD. So, and then let's first run it. Let's see what it does. Before that, as I told you yesterday, we need to add path to all the functions. Yes. So this matter still need to run first, so that we can add all the path to all the functions. Now I can go. I can easily do my stuff, and then I can run this code. Test underscore HK underscore IWD underscore edited. So for Bokaro, let's see first. So it is asking for which station. So count number is given, like 1 is for Bokaro, 2 is for ISM, 3 is for Sahibganj. So I want to do it for Bokaro. So total of 143 receiver functions are there in the folder for the data for the Bokaro station. And the best H value that we are getting is 44 at around 44, and best kappa value is 1.85. Now it will plot the contour map. Let's wait for some time. Looks like my system is slow, but it will generate the plot. I'm not able to actually from here it is not generating. Let me ask my PhD student to show you that. Dheeraj, Dheeraj, yeah, Dheeraj. Dheeraj, could you please share your screen? Am I audible? Here you are not audible. So he is my PhD student, Mr. Dheeraj Kumar Singh. So he is actually working on that computer already, because there is some X window issues on my computer. So I think he should be able to show you something from there itself. Uh, Dheeraj, could you please say something, because we are not able to hear you. There is a lot of noise. I think it would be better if you can exchange your microphone with someone else. Here we are not able to. So Dheeraj, what you can do, I suppose, you can take someone's laptop, come online from that there also, and share your screen from
Yes,
the.
sir.
Okay.
Hello.
Yes. Now you are audible. Please share your screen. Yeah, you did.
Hello, sir. Am I audible?
Yes.
Uh, okay, sir.
So what I would like you to do, just open your terminal
Yes, sir.
and go to Mukesh's home directory. No, I am asking you to go to Mukesh's home directory. I have actually pasted the path into the chat box. Please copy that and go to that direction.
Okay, sir.
Yeah.
Yes, sir.
Now open MATLAB. So now you can see Neeraj is opening MATLAB in Mukesh's home directory. Now run that code with this one test HKIW edited contour POKR.f. POKR.f.
Okay, this one.
Yeah, this one. Type 1.
Description 1. Okay.
Okay, first go to that folder, process RF MATLAB underscore master.
Process RF MATLAB.
The folder on top. Process RF MATLAB underscore master. Then run that code .m file.
Step.
Now go back again to the same directory. Just go to that test scripts
Okay.
and test depth mapping. And then run the code. dokr.m. Type 1. Oh, because you are actually opening his file from your own credentials. So is it possible for you to go Mukesh's system? Mukesh's, you can log in as Mukesh,
Yes, sir.
but I don't think you have password for it. You?
Yes, sir. I don't have password.
Okay.
Okay. Yes, sir. I have a password, sir.
I'm sorry, guys. There is some trouble, but I am sure it will work.
Sir, I have one question.
Yes. Yes. Sure.
So, sir, through this method, even there is one value for the Moho discontinuity underneath each station, right? Underneath each.
Yes.
So, how do you interpolate between stations? How do you interpolate between the stations?
There are many techniques available within the MATLAB itself. So those techniques can be used, like rigging interpolation is there. So that can also be used. There are many other methods available. I don't recall the name of all the
अब मेरा
methods
स्क्रीन
right now.
विजिबल है क्या?
So
मेरा स्क्रीन विजिबल है?
you can use any of the interpolation techniques. Your screen.
Okay.
What is there on the screen? But nothing is there right now.
Sir, again I have to log in. That's why.
So you didn't log in as Mukesh?
Mukesh, sir, directly I'm logging again with my email.
No, I am saying you should log in on Earth with the credentials of Mukesh.
Yes, sir. I have logged in already.
Okay, show us the terminal. Did you share the screen?
Actually, I have to join from here only because screen was already shared, but that is not working at this point.
Okay. Yeah, in Mukesh, it is not working, but with your credential, it is working.
Yes, sir.
Okay. Okay, guys, I think that is fine because the contour map that you will see will be looking something like this only. Okay. So, but we'll be having different value of H and kappa. Okay. Because we are using stations data from different stations. So I think that should be fine. Now, and also like for ISM station also, we can do the same thing. Okay, so let's forget about the contour map because we are still getting the best H and K value that is actually popping up on the command window itself. So what I am going to do, I am going to share my screen now. Just stop sharing your screen, Dheeraj.
Yes, sir.
And get yourself ready for ambient noise. Okay. So in the
Okay, sir.
so log in back again. Okay. So stop sharing. Okay. Now so you can see now I will run the run it for ISM station. And I like 2, and you can see total number of receiver functions are there is a count of 204, and the best H value is coming at around 42, and best kappa value is coming at around 1.91. And yesterday only, I have shown you the data on which I am running all these uh, processing steps. So like we have shown you what was the data. So data is there. So for ISM, I have shown you all the receiver functions. So we have also made a plot. So this is the gather for ISM station on which we have run HTTP stacking. Likewise, we have gather for Bokaro station on which we have run the stacking. So this is the gather for ISM station on which we have run the HTTP stacking code. Okay, so now what we are going to do, we are going to start with ambient noise processing. So for ambient noise processing, we will see how the seismic interferometry and the cross correlation can be performed. For that purpose, there is this code that we are going to have the glimpses for today. This one, yeah, this one. So I am just copy and pasting the link to this code, which is available on GitHub. And there is a paper also which was published on this particular course. So here is the paper. This one, the title of which is Relative Group Velocities at periods in between 6 to 23 seconds across Brazil from ambient noise graph. So this paper you can read. The link I am posting on the chat box. So for this purpose, what I am going to do, because Dheeraj has been working quite from some time on this code, so he will give you a kind of glimpses of this code to you right now. Okay, so Dheeraj, are you ready?
Yes, sir.
Did you change your change it to your own login with
Yes,
your
sir.
own?
Yes, sir.
Okay, just share your screen. I am stopping sharing.
Is my screen is visible to all?
Yes.
Uh, Okay, from here we'll be starting the ambient noise tomography, and for that part we'll be discussing about cross correlation calculation. In cross correlation, basically we'll be focusing on the green function, and then after the dispersion curve. So these two will be our prime focus for our discussion. So here I have made a folder, uh, GIAN folder. So in this, we'll start with the basic data processing, like how we get raw data and how to process that raw data. So basically, for that, I have made a folder that is one J component. So in this folder, as you can see, there are various files. Like one is named with a .sci, and other folder are like Jet Agat and Jet Balloon. These are basically the station name that we'll be discussing about. So our data, when we'll be acquiring some data, so our data will have different formats like RAFTEC format or in Gural CGF format, or it may have MSID format. So basically for this code, for Guttaway code, we need the data format in terms of MSID, dot MSID. So our primary focus will be converting the RAFTEC format to SISON format, and then after SISON to MSID format. So whatever format, finally you need to get data in the MSID format. So for before starting the process, we'll have to inspect the data and what is the what is present in the data, and what how much count is present in data. So we'll have to see that. So for that, we'll start. Derf star.sci is a listing command. So from this, we can list the whatever present in our terminal. Like I have listed the file which has extension .sci. From here, we can see. So is it visible to all?
Yes.
Yes, yes.
Okay.
So what kind of
So
software it is? This on which you are showing all these three seismograms?
this is SISON, sir.
Okay, okay. So
This is
please let everyone know about all these things.
yeah. I have opened this terminal in the SISON, like with the command like derf star.sci. As we have seen, derf star.sci for the listing the SISON file, and then after mulplot, mulplt, that is mulplot command. So it asked us what file number we want to open. So I want to open the first file number, so I have given the option 1. So next, it listed the that file number, that is 2016, and the Julian day is like 366, and then after hour, minute, and second. This is, and Tura is generally the station name. So then after we'll have various plotting options, like if we want to have interactive picking, so we'll have directly put the inter, and if we need the multi-trace plot on the screen, so we'll put 0, that is the default option. And there are too many other options for interacting with your data. So next option, suppose I have put the multi-trace plot on the screen. So I have put one, and then after, so it will ask about the filter, whether you want to apply some filter on your data. So like a low and high cut filter, if you want to apply filter, so you'll have to put the low at first, the lower limit of your filter, then after the higher limit of the upper limit of the filter. So because we want data to be observed in raw format, so I have not applied any filter. So now you can see here. So this is your Sison window. So here you can see this is Tura BZ. As we have in previous classes, we studied that this is a station name. B is for the broadband, and Z is for the vertical channel. And similarly, this is for broadband northeast north-south channel, and this is broadband east-west channel. So as we can see, also we can observe this data in the different frequency band. Like suppose if you want to apply the frequency band of 1 to 5, so that is 1 to 5 given here. So after clicking on the 1 to 5, so we'll plot. So this data now looking in, now we are observing the data in 1 to 5 frequency range. So similarly, we'll have to see in other, we can observe it in other frequency band also, like 5 to 10 hertz or 0.1 to 1 hertz. So as you can see, so you can ask why we are observing this in different frequency range. So when we are talking about, or when we are studying or working with ambient noise tomography, we are just avoiding any earthquake event. Okay. So if there is an earthquake event, we'll have to tackle that event. We'll have to remove that earthquake event. So that's why we are observing this data in the different frequency range. So as we can see, there is no earthquake event in that in this window. So similarly, other window also we can check. So we have observed raw data in the raw format. Now the next process will be splitting this data. So as we have seen, so when we have observed the data in the Sison format, it had three components like vertical component, north-south component, and east-west component. So, but for the ambient noise tomography, we need only vertical component because there is a clear presence of the relay wave in the vertical component. So, for that, we need to split this data. Like, so, so it had three component. So we'll have to split, and we need to extract the vertical component only. Okay. So for that, we'll do. For that, we'll use the command that sci. Okay, that is for the splitting. Is my screen is visible to all?
Yes.
Uh, okay. Next, we will use the command sci for the splitting this seismogram. So I have listed these seismogram like 1, 2, 3, 4, and 5. Now we will be splitting this. So for that, command is sci. So now after striking the sci, so we'll get two options like merge one or the split. So which option we need accordingly will be moving forward. Like we want to split this data, so we'll strike two. So what format we need? So as for the ambient noise tomography in the Guttaway code, we need data in the MSID format. So for that, we need will we convert that Sison format into MSID format. So this is your MSID. So which file you want to split? There is the option. So I have five options, like from 1 to 5. Or other thing is that I can convert all those things or split all those files. So I'm splitting the first file, that is one. So now our channel, our seismogram has been split into the three channels. As you can see, this is vertical channel, and this is north-south channel, and this is east-west channel. So if you want to split another one like second, then you need to enter 2. So now second seismogram also split it, and similarly 3. Okay. Or if you want to split all at a time, so you can enter like a file nr.lis. Okay. So it has splitted all the seismogram. As you can see, earlier there were 5 files named as .sci. Now there are many files with a separate name like vertical channel and north-south channel and east-west channel. So in the next step, we'll be separating all these things. So as we have separated, we will be working for the two station. So that is Agat. Agat is one of the station, and the other station is Belon. So I have put here a vertical channel of these stations, as we can see how it looks like. Or also we can see the how the single channel looks like.
So that means Agartala, Balon means Balonia. These are two stations which are located in northeastern India. So data we are currently working upon is the continuous data from northeastern India.
So now we can see there is only one channel. Earlier it was three channel, all these three channel, but now we can see only one channel. So now our channel has been splitted. So now we can separate this. Like this was our basic steps of the data preparation, like how to get the vertical channel. Okay. So we'll be asking about why we need to see all these channels and what is the benefit of observing the data like this. So here we'll get the answer. Like see, this window shows your data information, like what is your the plot start time and what was the time of the data and what is the channel name, that is BZ is channel name and the Agat is station name. So as we can see, for the 3 hour and 20 second and 20 minutes there is a data. For the next 3 hour 3 hour and 21 minutes there is no data. Another is 4 hours and at 4 hours there is no data. So by observing this raw data in this format, we can observe whether there is a data present or not. Okay. So this is the primary purpose of the observing the raw data in this format. So next, this was our the first this was the first things we need to do. So we had taken the data in the raw format, and we have converted that into the SISN, and then after MSIT format, and then after split that MSIT format and get the vertical channel separate. So next we'll prefer to do the prepare the files that is needed in the Gutenberg code. Like we need some data list file or the station XML files, and all these files needed for the instrument correction. Because as in earlier lecture, we studied about when in the cross correlation, we need the gain function of the Earth beneath between the stations. Okay, so we need to remove the instrument response. So for that, For that, we have various files like you can see. So as you can see, for the preparation of the two files, as it is named, that is the data less seed files, and other is the station XML file. We need various information of our stations and what type of instrument that is present at the station, and what is the location of the station, like the latitude of the station, longitude of the station, what is the deep at the installation place. So all these things we need. So the first will focus on the seeing the instrument response. As we can see, this is you know a pole zero file of an instrument that is for the Raftec instrument. The instrument name is Raftec 151 122nd, and then it has a sensitivity of the 200 2000, like 2000 volt per meter per second, and the natural period is 122nd, and that is normalization factor, and other is normalization frequency and the number of zeros, number of poles. So all these things will be listed in your instrument response files, and this file will be provided by the manufacturer only. So using this file, will be prepared the dataless seed file and a station XML file. So here, so as you can see, this is the dataless seed file, and so this file will be needed uh, for working in the ANT. This file you will have to prepare. In this, what we put the various things like network code, and so network code should be two-digit of the two letters only, and the station call letters should be maximum of 5 letters and minimum of 3 letters, like that, and the site name that is the given, and the latitude that you need to put, longitude you need to put, and then after when your station has been started and what is your instrument there, and next thing is for different channel we need to append all these things: latitude, longitude, and elevation. Okay, you can have different elevation, latitude, and longitude if you are using the single channel seismometer. Like suppose earlier people used to have a single channel seismometer. Then we have latitude, longitude, and elevation. The latitude, longitude, elevation for each channel would be different. So we'll have to prepare three files like this. So next, so we have put the latitude, longitude, elevation, start effective date, and the end effective date. All these things has been appended in the blocket of the MSID file. That is, blocket number is 50. This 50 is the blocket number, because in MSID data everything has been assigned as a certain blocket. So different blocket has a certain criteria. So in 50, up to from 50 to 60 blockets, we have the instrument response parameter. So accordingly, we have put up these parameters. So next, we'll put the pole. As we have seen the pole zeros file that was provided, which was provided by the manufacturer. So it has 4 poles. So accordingly, I have put the 4 poles like this one. So other thing that we need to be very cautious about the what sign we are putting. So if there is a even if there is a sign difference between these poles, so it won't work properly. So this the pole has been put here, and then after that is a imaginary pole, imaginary part of the pole. Then after, what is the error in observation of the pole, and then after similarly zeros, what zeros are present. So you can ask you why, from where we'll get the poles and zeros, and how do we how can we get the poles and zeros. So for getting poles and zero, we need to have some transfer function of the instrument. Okay, for poles and zero, we need to have transfer function of the instrument, and when we get the transfer function of the instrument, we have Fourier transform of the output by input. So we'll get some expression in the nominator and other expression in the denominator. When will be expressing the nominator or equating the nominator with the zero, we'll getting the zeros. And when we'll be expressing the denominator with the zero, we'll getting the poles. Accordingly, if you are making any system, so you need to have transfer function of that system. Accordingly, we can identify the poles and zeros of that system. So other file we have like uh, station.py files. So this file will be needed for the preparation of the station XML file. Okay. So this file is similar like the data less sheet files. So for the instrument correction, you can use either of these, either data less sheet files or pool or station XML files. But there is a column of the depth, azimuth, and the deep of the station in the station XML file. But in case of data less files, we don't have an option of elevation, depth, and azimuth of the file. Okay, so there is a better handling of the instrument response by using the station XML files. That's why we use the station XML file for other data for instrumental correction. So here also we can observe. So we have the network name and code of our station and latitude, longitude, elevation. So and one more thing, and this naming of your stations must match with the must match with the seismogram that we have seen in the section or in the vertical component. If it doesn't matches with your seismogram or vertical component seismogram, so this file will won't work and your code will not work. So other thing we'll have to provide, that is sample rate. So it needs sample rate. So normally we are using the 40 sample rate of 40, that is 40 samples per second. And so next other thing is what sensor keys and the data logger keys. So sensor keys is all about the sensor, what type of sensor we are using. And next is data logger keys. That is what type of digitizer we'll be using. So what characteristic of a digitizer will be using? That is data logger keys. So after putting all these things, we can prepare a file and write that file using Python, like inv.write, and what will be the name? That is zorha.xml. That would be the name, and the format will be the station XML files. So as we have seen, we had two files. One is dataless.py, another is station.py, and so there in station.py we have a special option like a deep of the station, azimuth of the station, and the other is about the data logger keys. So when we are when we are correcting our seismogram for the instrument response, we need to have information about uh, seismometer and the digitizer also. But sometimes we observe that the seismometer digitizer is inbuilt in the seismometer, so we need to worry about only seismometer and the configuration that is put in the seismometer. But in case digitizer is different, so we'll have to see about how the conversion is happening. Like suppose seismometer has a rating of 2000 volt per meter per second, and digitizer has something like 2.3 microvolt per count. So accordingly, we can convert those voltmeter per second into the counts. So if we are not putting those value in the data logger keys, so we will be not getting the exact amplitude of our seismogram. So what we have seen, so we have taken our raw data, we have splitted that data And we have separated the vertical channel. We have observed the raw data for the presence of data. And the next thing, we have prepared a data list sheet files and then station XML files. Now, what we'll do, we have so as we can see, we have vertical channel of 1 hour length. Okay, as we can see that is this is of 2016, 540. That means 5 hours and 40 minutes. Next is 2016, 6 hours and 40 minutes. That is each file contains 1 hour of data. So when we will be working in this code, so we'll have to merge this data for the 3 months. Okay. So the next thing we'll do, we'll be merging all these vertical components. Okay. So uh, after merging, we'll get like this. As we can see, this is the code for the merging the seismogram, merging the vertical component to the seismogram. So here we can see, so what we are doing, we are importing some tools from Python like NumPy, OffSpy, and Raid and Matplotlib. So from here, I'm reading the data like where my data has been put, like home, dealers, products, like that. I have put the data here. Next, what we'll do, the st.merge, and we are using a certain method like method 0, field 0, and interpolation sample -1. So what it says, so our data may have some gap. So for filling that gap, we need to we need to have certain values. So we can put either averaging of the from averaging of the value on either side of the gap, or some another method. So similarly, we can make the data more continuous by interpolation, by interpolating and then writing in the form of like this: any Mokosi, BHZ, and MC. So these data should have the similar format like the network name, station name, channel name, and then after .mc. So what we have performed, so we have got our data and merged those data and applied the instrument correction or prepared the instrument correction file. Next, we have to do, we have to change the configuration file. So, so why do we need to change the configuration file? Because we have different, we have to calculate cross correlation for the different period range. So accordingly, we'll have to change the configuration file. So now, at first we'll see the after merging those vertical channel how data looks like. Okay. So offspy scan is a command in the Python that is used for the to know what percent of data is available in our file. So as we have seen before, as we have seen in the file in the session, so there were some gap in the file. So after interpolation, so we now have a continuous data. So now the data fill is 100%. So when we'll be observing in the configuration file, we'll have to put the amount of data fill that is present in our configuration file accordingly. So if we have 100%, so we can put a data fill value like 0.99. So if we suppose if there is a data gap in our file seismogram, so we'll have to, accordingly we have to full fill the value like 60%, 70%. Accordingly, we can vary. So next thing we'll be observing the what headers are present in the data. For that, we'll have to go in Python. Uh, Import OpsPy from OpsPy import read. So now we'll be reading the data. So we'll be assigning a stream to our data, and then after a read, we'll have to give the path of our data, like and the name of the file. So stream has a different. This is type of list. We're getting the many things, so it will be listed in some count. So we can observe the first count, like we'll using the first sample. So for that, so we are doing. So now you can see here we can see the header of the data. So as we can see, what are the stats of the data, and that is the sampling rate of the data, that is 40 sample per second. What delta we are using, that is 0.025 second. What was the start time, in time, and the number of point, what number of point present in the data, and what is the network code, and what is the station code, and what is the location, and the channel. Actually location one, so there may have different location, like named with a different type of channel, like primary channel and the secondary channel. So it can have various locations. So next is channel, that is the BZ channel. It should be similar with the seismogram that is seen in the Sison window. And next is what type of data it is, that is MSIT. And then after data quality, and then number of records. Similarly, we'll get like this. And the record, what is the record length? All things will get here. So here we can change this also. So our data is almost prepared. And next we'll change the configuration file according to our needs. So there are various parameters in our configuration file, as you can see. So basically there is a five things like the paths, maps, cross collision, and F10. So we'll be processing up to F10, that is up to the dispersion curve. So as I have read up to that part only. So for this, we can at first we need to specify the path. Okay, so where our data is located, that is put in the MC directory, and where I have put the station XML directory, and where I have put the data list directory, all paths need to be given. Next, we'll have to put the paths of the output directory, like where I have put the output of the file, like output cross correlation directory, output of the F10, output of the tomography, and then output of the depth models. So next, if you have some maps, like you can say if you are working in certain region and you have made some maps using QGIS, so you can accordingly put the coast SHP, Tecto SHP, and Tecto labels. Okay, if we don't have map of that region, so you can put blank here. Or next thing, you can put colors according to the geology of that area. Like if you have Archean, so you can put like this. Accordingly, we'll get that in geology part. So next we'll have to put, so we'll have to put certain boundary of your data, like your box is from that is longitude minimum is given, that is 88, and maximum longitude is given 96. Similarly, minimum latitude is 20 and maximum latitude is 30. So accordingly, it has prepared a big box, and inside that, our study area has been put, that is extending from longitude of 89 to 95 and latitude of 22 to 29. So these things you need to change according to your area. So next thing, for the cross correlation part, we need to change all and change these things, like whether you are using data list PZ files or the station XML files. If you are using the station XML files, the put true here. If you are not using the station XML files or and using data list file in C, so you can put in true here. Or also you can put true in both of you, and the program will accordingly decide. And next, our data had duration of first month. So I have put that is first day of first month of 2016, and the last day is 31st day of first month 2016. So this is the minimum field that I have talked earlier. Like when we are observing the data, so it can have a field, it can have a various gap. So that accordingly, data field may have the 50%, 40%, 70%, 90%, or even 100% you can get. Okay. So because for this, we need continuous data. For ambient noise tomography, we need continuous data. So we need to have a maximum field. Okay. So we need perfectly continuous data. So generally we put uh, those data which have a good field, and you can take a criteria like it is above than 60% or 60%, or you can put 100% also if you have a good data, very good data. So next is the cross correlation and the station subset. And in this, what we have, so if you are using all the stations, so you'll have to put null in case you are using certain subset of station. Like suppose you have a 10 station and you are using only 6 of them, so you need to have a put subset of those station in the square bracket. Next, cross correlation Tmax. So it shows the maximum time window of the for the cross correlation. So up to this maximum. Hello, am I audible?
Yes, you are audible.
Yes, sir. So 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 it shows the cross correlation Tmax, that is the maximum time window for the cross correlation. So I have put here 2000. So at a time it will cross correlate for the 2000 seconds. So similarly, in bandpass parameter accordingly, we can put like the 3 to 30 second I have put in. Then after corner frequency, that is corners to that is it is decided from where our energy has been dropping. So accordingly, we have put the 2. So what type of wavelet we are using? That is a zero phase wavelet. It will be using. Next, the period sample, that is decimated to 1 sample per second. Earlier we had 40 sample per second. Now it is decimated to 1 sample per second. Next is 1 bit normalization. Here I have put the false. So you can put true. Basically, it need to be put true, because if there is an event, as when we were observing our raw data, if it has an event in any frequency band, so we need to put 1 bit normalization as true, because 1 bit normalization has a beauty that it can give you good ambient noise tomography raw data by removing the earthquake event. So or accordingly, we can put the earthquake periods and band. Suppose we are observing the earthquake in certain frequency, so accordingly we can put here. And next is window frequency. So this was all about the cross correlation. Next is Afton analysis, like for the dispersion curve. So we'll be calculating dispersion curve in the different period bands, like 4 to 7, 7 to 50. But these bands will be focusing on the middle of the period, middle of the band, like 4 to 7 will be focusing on the 5-second period, and 7 to 50 will be focusing on the 10-second period, like that only. So So next is the signal window. That is signal window and the noise window will be decided on the basis of the station to station distance and what is the maximum velocity, maximum phase velocity available in that area. Accordingly, that is it is t should be greater than distance by the V max and less than distance by the distance by V minimum. So next is noise window. Window will, suppose we have our signal window. Then after we will use next 500 seconds for the noise window size. Next is period and the velocity of the Afton, that will be given at the start, stop, and step. That is raw Afton, that will be calculated in the period band from 3 to 4.45.1 hours, and will be with the step of 1. Similarly, that is clean Afton will be calculated from 3 to 45.1 with step of 1. And Afton velocity will be starting from the 2 to 5.51 and with a step of 0.01. And Afton alpha, this is Afton alpha. This will be used for the attenuation and the strength, attenuation and the strength. So Afton alpha will be using for 20 here. So next is we'll be discussing and will be have whether we'll be using the maximum instantaneous frequency or not. So if we are using instantaneous frequency, so we'll put true, otherwise it is false. Next is maximum relative difference instantaneous nominal period, that is given as a 0.5. So accordingly, this parameter you need to say according to your data.
Dheeraj, presentation is not visible.
Sorry.
Presentation is not visible.
Okay.
Please share your screen again. And now please move on to the cross correlation and the dispersion curve.
Okay, sir. Wait. Okay, so I was talking about the changing the configuration file. Is it visible now?
Yes, it is visible.
Yes, yes.
Yeah. So in case we had to change the certain things in the configuration file, like we'll change for the path where our data was present, where our station XML files, and where our output file is located. So all these things we need to put in the path folder, and then after, if our QGIS map is available, so we'll have to put the certain parameter here, like post SSP, tech to SSP, tech to labels, like that. And if we have a geology, if we have an idea of geology of that area, so accordingly we can put certain prepare a QGIS map for the geology. And next is we'll have to put the latitude longitude bound for our station. And next is in the cross correlation, we'll have to put what file we'll be using, like data list PZ file or station XML file, or what length of data we are using. We are using for the 1 month data, so accordingly we have put like this. So after changing the configuration file according to our data, so next, so we have prepared our raw data, we have changed our configuration file. Next, we can run the cross correlation. We can compute the cross correlation. So after running, it will ask for the what file it will use, what configuration file it will use. So it is asking for the configuration file because it has only one configuration file. So it will automatically take that configuration file. In case you have the two configuration file, it will ask which one to select. Accordingly, we have to select the configuration file. So now the cross correlation process is running. So each day it is running uh, at a time. 1 day cross correlation is being calculated. So as we can see, at some station it is skipping and writing like only 0 it is skipping. It means that we don't have the filling criteria. So in the configuration file, we have put like 60% fill. If it doesn't matches the 50% fill, it will skip, or it will find zeros only, then it will skip. This will take some few minutes.
Neeraj, are you there?
Yes, sir. Yes, sir. So now cross correlation has been completed. Now we can observe this in the output folder. like as we can see, the cross collision has been computed for the different station pair like Agartha and the Balon, Agartala and the Balon station, then Agartala and the Jorhat station, and Agartala and the Moko station, and Balon and Jorha, and Agartala and Mokochunda station, and the Jorha and Mokochunda station. So we can see. So as we have studied in the earlier lectures, like cross collision, as used to compute the gain function between these stations. The gain function for the Earth between the station point. So this cross collision can be plotted. So the plot will be looking like that will be seen that after running the dispersion curve. So also we can prepare a plot like this. So to see whether where the cross correlation is action. So as we can see, it is best cross correlated at this value or this time we can say, because it's a zero phase, so it will be observing the maximum amplitude at the zero only. So after calculating the cross correlation, now we will run the dispersion for the F10 analysis or the dispersion dispersion code. So So it is asking for the input. So we have cross correlation computed. Now we'll have to put the input. So because we have the response file part of the cross correlation, so we'll put the input. So it's calculating the dispersion curve for the different station pairs. Now we can observe the result. So now you can see. So this is this dispersion curve that has been computed. So we can see there is two types of dispersion curve that has been shown. That is one is a raw dispersion curve, other is a clean dispersion curve, as you can see. So this one is the raw dispersion curve, and this one is clean dispersion curve. And what are the concept of the raw dispersion curve and the clean dispersion curve? There has been used a phase match filter, and by using the a phase match filter or anti-dispersion filter. So when we are getting the seismogram, so the every phase is dispersed. So we put the anti-dispersion filter, and then after we remove the certain noise near our signal, or you can say the gain function of the cross correlation. So we remove that, and then after we again disperse the signal and calculate the dispersion. So that becomes the clean dispersion curve. So as we can see, this is the raw dispersion curve, and this one is clean dispersion curve. So there become some differences. So energy energy dispersion, or you can say velocity at the different pairs can be seen. Although it's not that good, but we can correct this by yeah, filtering our data with a meta or with the better view, or you can see by using the better data. So also you can see here the gain function that uh, is calculated by the cross correlation process. And here this is the station for which the dispersion curve has been computed. Like Agat-Johar pair, the dispersion curve is like this, and Agat-Mokosi dispersion curve is like this. And similarly for the different station pair, we'll be getting the dispersion curve.
So I think that is all from Dheeraj's side. So thank you, Dheeraj, for the details that you have provided on the cross correlation and the dispersion curves using the Gutenberg code. So the PDF just here have shown you one acknowledgement we should actually make out here is that the dispersion curves that were computed for some of them, it was not of good quality. Maybe because there was a lot of gap in the data and we were using only maybe 1 month of data or so. So to make better dispersion curves, you will have to use maybe the larger period of data, maybe for 1 year or 2 years of data. So after using that number of data, then only I think you would be able to get good dispersion curves. Because our main motive here was to show you just to the example how to process the data in the Python environment using the Gutenberg code. So we were pretty successful in that. But if we would wanted to use like 1 or 2 years of data, then you can see like for 1 month for calculating the cross correlation, it was keep on running and it took almost around 3 to 4 minutes to do all the cross correlation for only 1 month data. So likewise, if we were to show you the 12 months of data, then you can multiply it, like it might have taken half an hour or 1 hour or so. So that was not feasible at this point, I would say. So one thing that you must remember that as much as data you have, better the dispersion curve would be, better the cross correlation and these functions would be. And you may not want to have a lot of gap in the data because you will end up having a lot of interpolation into the data, and that will create problems in the computation of the dispersion curve. Sometimes what happens when you are keeping your instrument in the field, then due to some technical issues, or maybe the area has been covered by some maybe flood or something, then uh, it may uh, badly affect the instrument's health, and then instrument will stop working. So in those cases, sometimes it may happen that the data is not being recorded for a period of time. Then when some technician visited the location, then he may fix the issue with the station, and then the instrument will start to work again. So that is why those kind of gaps may be seen on the data. So that is what he was talking about, that the 60% data minimum should be available to do the cross correlation, but it would be better if you have more than that. So like if your data, if you have 90% of data or 95% of data available with you, then it will be better. But those unfortunate things you cannot avoid, because you cannot control all those things like flooding, and sometimes due to some technical problems, the instrument is not working. So in that case, you can't do much about it. But if your area is good and your chances of getting the data is continuous data correctly is good, then you may end up in getting the good dispersion curves out of your data and the good cross correlation out of your data. So, is there any question so far for me or Dheeraj?
Yes, sir, I have some questions.
Yes, please go ahead.
Sir, what is pole and zero in that coding?
So, Dheeraj, would you like to answer this question?
Yes, sir. Yes, sir. Sure, sir. Hello.
Yes, we can hear.
Hello. Yeah, Santan. So, as we know, every system has some transfer function. So we put some, suppose a system, we are putting some signal into the system and we are getting some output. So the so poles and zeros is defined as like that. So we are taking the Fourier transform of output by input. Okay, so we'll have expression. After doing this, we'll have some expression that will have some nominator, okay, and denominator. That will be in the fractional form. So some it will have some nominator and a denominator. So when we'll be equating nominator to zero, so whatever the value of variable we are getting, that is called zeros. And the next, when we'll be equating denominator to zero, so whatever values we'll getting, that is called poles. Okay, so these things are these things define certain frequency band in which our instrument is operational. So these things just restrict your instrument or the electronic unit for recording in the certain frequency only. This is the main purpose of the poles and zeros.
Okay, thank you. And one more thing is, what is that configuration file?
So configuration file contains whatever it contains the various sections like what is the path of your data file. Okay, so what parameters you will be using for your cross correlation, what parameter you'll be using for the calculation of the dispersion curve. So for in path you will be putting where is your data located, where is your instrument correction file is located. So next is what maps, what are the path of the map file or the QGIS file or .shp file. So you need to put information about all this in the configuration file. When any of the program in this code is running, it will take input from that configuration file and then after it will proceed.
Okay, okay.
Is it okay?
Yeah, it's good. And one more thing, so in this thing you are combining codes from MATLAB and Python, or MATLAB was entirely different from Python?
So actually we have not used any MATLAB, I think. So we have used only Python only.
Yeah, MATLAB was used for edge-compile stacking and the receiver function, and Python is used for the ambient noise processing.
Okay, sir. Thank you.
Actually, we are getting you introduced with all these MATLAB, Bash script, and SAC, and also the Python, so that you can have diversified set of knowledge about what are the tools available in seismology that can be used to do some kind of processing and also to compute some kind of information out of your seismogram. So that was the main motive.
Okay, sir. Thank you.
So any other question from anyone? So I hope there are no more questions. So this was end of today's tutorial, and also the end of day 9. That means we are going to heading up towards the test tomorrow, which will start right at 7:30. And as I told you previously, the test will be taken from Google Form. Almost around 15 questions will be there, and the maximum marks that you can score is 100. And you should be very much punctual in completing the test, because right after 9:30 the form will stop accepting your responses. So be aware of that. Try to submit your response little before 9:30, so that you should not miss out on the test. And a mark sheet will also be provided with the test after we will evaluate your answer sheet. So be careful, and also for solving the test, you may have to upload some of the answers. So keep a blank sheet of papers and a pen with you, and good mobile with you so that you can take the picture and upload your answers. So we have given enough time to solve all the questions, 2 hours for 15 questions. So it will also account for, that includes also the uploading time, taking the pictures as well. So be prepared and look at all the notes that has been provided to you. And my from my part, I am going to give you only 4 questions. 11 questions will be from the part that has been taught by directive. So with this, we are going to end all the lectures, all the tutorial we have completed today, and I hope you must have enjoyed all the lecture. Still, if you have any doubt, you can always email me or direct so that your doubts can be cleared out. And I am still in the process of uploading the video. As soon as I will do so, I will send the links to you. So that is all for today. Thank you so much.
Thank you, sir.
Thank you, sir.